Hello, today we will talk about the framework of the auxiliary group and what does the title Two Birds with One Stone mean. So as an example, we start with one of the earliest models which used flavons to construct tri-bimaximal mixing, and this paper by Alterelli Ferruglio, and it used A4 as the flavor group and consisted of two triplets which are irreducible multiplets of A4. Here what I have shown is a schematic diagram of the vacuum alignments of these triplets. So one of the triplets, it has a vacuum alignment V1 with components AAA, and another triplet has the vacuum alignment V2 with the components B00. The first triplet couples in the charged electron sector, and the second triplet couples in the neutrino sector, and the authors showed that this setup leads to tri-bimaximal mixing. Now the issue here is that when you construct the potential with these two triplets and include the cross terms, the specific alignments that we have here will be spoiled. And therefore, the authors put forward a mechanism using supersymmetry and extra dimensions to ensure that the cross terms are avoided. On the other hand, we can solve this issue using a group extension. Here we have a couple of papers by Holtersen, Schmidt, and Lindner. So these papers are also constructed using the group A4. However, they extend the group to a larger one, which is Q8 semi-direct product A4. And I have in the right side the schematic diagram of the vacuum alignments of various reps we have in this space of Q8 cross A4. So we have a triplet. Its vacuum alignment is U1, AAA, and there are two quartets. The group Q8 cross A4 has quartets as reps. So we have two quartets here, and its vacuum alignments are U2 with P1, P1, P2 minus P2, and U3 with Q1, Q1, Q2 minus Q2. The authors showed that if we write the general renormalizable potential with this triplet and two quartets, we obtain these as the a minimum. And here they include all terms, including the cross terms, and they show that these vacuum alignments remain unspoiled. Now they take the tensor products of these two quartets, and it turns out that the tensor product leads to a triplet of the form B00. Also, the other triplet here corresponds to the triplet of the form V1. Now you can use these two triplets and plug it in your A4 model and basically obtain a tri-bimaximal mixing. So what the authors achieved here is that using group extensions, they have prevented the problem of bad cross terms. So by the word stone, I mean the use of a group extension, and here the bird that we have got is that we prevented bad cross terms. Now let me talk about the second bird. Here is a paper that I had a few years ago. This is an S4 based model. We have several errors of S4 in the model. In the diagram, I have shown only one of them, which is a triplet of S4. What I had found was that if you assign this specific values as the vacuum alignment of the triplet, it leads to nice phenomenology. I get reactor angle and solar angle in excellent agreement with the observed experimental results. However, if you construct the potential of S4, we are not going to get a minimum that corresponds to this alignment. Of course, we can tune the parameters in the potential and get whatever minimum that you want, but that is not correct. In fact, if you tune the parameters, then it is simply you are shifting the problem of the phenomenology to a problem of fixing the parameters in the potential. So we don't want to do that. In order to obtain this highly non-trivial alignment of the triplet, I used a mechanism very similar to what I explained previously, that is the extension of the group. So as I stated, I have an S4 based model. Now I extend that to a larger group. I called it Y4. I'm not going to explain what that group is, it's not important. Now in that space of the larger group, I introduce three errors, and their alignments I am showing it in the diagram as U1, U2 and U3. Again, here I am not showing exactly what those alignments were. Now I take the tensor product of these three reps and I get a triplet of S4, and I show that the alignment of this triplet is in this form: minus a, minus 2 root 6a and a, and then I plug it in my model and get the nice phenomenology that I wanted to get. Regarding the alignments of the reps U1, U2 and U3, I can show that if I construct the potential of these errors individually, I get these alignments U1, U2 and U3. On the other hand, if I consider the cross terms, then these alignments will be spoiled. So in this model, the problem of cross terms still exists. So here I'm not using group extension in the way it was used previously to prevent bad cross terms. Here I used it to get specific constraints among the components of the triplet of S4, which I wouldn't get otherwise. So this is what I call the second bird that you get using group extension. You can get specific constraints among the components of an erupt so that we get nice phenomenology. Here I have the schematic diagram of my new paper. On the left side, you see a group GR. I have three erupts, V1, V2, and V3 in this space of GR. On the right side, you have the group GF, which is a larger group, which is the group extension of GR. And I have 7 erupts in this space, U1, U2 to U7. I take the tensor product of U2, U3, U4 and obtain V2, and I take the tensor product of U5, U6, U7 and obtain V3. And U1 directly corresponds to V1. So this is the structure of the model. I construct the general potential involving the errors U1, U2 up to U7, and I show that the potential has the required minimum. I also consider all the cross terms and show that they will not spoil these required alignments. In the space of GR, if we consider the alignments V2 and V3, we will get highly non-trivial constraints among their components, which is the result of these being obtained as a tensor product of irreps in the larger space GF. As I stated in my previous video, the model is highly predictive. It predicts all mixing angles and the CP phase. It predicts the lightest neutrino mass to be very, very small, and it also predicts the ratio of second and third mass eigenstates. So all this prediction is because of the highly non-trivial constraints among the components of V2 and V3. In other words, the group extension gets me both the birds. I prevent the problem of bad cross terms, and I obtain specific constraints among the components of irreps in the space of GR, which leads to very nice phenomenology. Before I wrap up this video, let me give you a little bit of information about the group extension. On the left side, we have the flavor space of the fermions. I call the corresponding group GR, R indicating fermions. And on the right side, I have the full flavor space. I call that group GF, F indicating flavor. And GF is a group extension of GR. The fermions transform as an unfaithful representation of the full flavor group GF. That is the reason why GF is a larger group than GR. When we have an unfaithful representation, we obtain a non-trivial kernel. And this kernel turns out to be a normal subgroup of the full group GF. This comes from the fundamental theorem on homomorphism. In this construction, I call this kernel, which is a normal subgroup, the auxiliary group. So when we have a normal subgroup, we can take a quotient. So the quotient of the full group GF with the auxiliary group GX is nothing but a group which is isomorphic to GR. So that is what is shown here. GR is the quotient of GF by GX. Another way to say is that GF is a group extension of GR by GX. So that's the notation here. I have used dot here to indicate group extension. This is the convention that I see in some of the references. That's all for today. We will discuss more in the next video. Thank you.